All right, so as we move on to 10.4, now we're doing areas of regular polygons and composite figures. Don't forget, regular polygons has the same number of sides, equal sides, and congruent angles. And composite figures is where you put in more than one shape together in order to make it. All right, we've got a lot of new vocabulary today. The center of a regular polygon, well, basically if you look at the diagram over here, you've got a regular polygon, a pentagon in this case, and the center of the circle that touches every one of the points is the center of the regular polygon. The radius is going to go from the center to any part on the outside, but if it's touching one of the angles, the vertex of the segment. And then the apothegm is a new one that we've never had before. Okay, the apothegm is where you can create a triangle from the center to the two sides, and what if you bisect the angle and go and make it perpendicular to the side, so it's going halfway from A to B and it bisects P. That is called the apothegm. And it does change the formula that we're going to be using a little bit later on. Alright, so now we're coming to the very basics of what they're asking you. In example 1, all they're asking you to do is identify various parts, but let's have a look at the rest of the information you're interested in. First of all, it's a regular heptagon. That's a 7-sided figure where all the sides are congruent and all the angles are congruent, and that it's inscribed within the circle P. Okay, so let's have a look at what we've got. We've got several things, so let's give them letters. All right, so A is going to be the center, so identify the center. Well, the center is a point, so make sure you write point P. Okay, it's different from the center of a circle as we've been given in the information. The radius, you've got two radii here. You can either have PB or you can have PC. Both of those go from the center to one of the vertex of your heptagon. The next one is the apothegm, and remember what I said about the apothegm. It's the line that bisects the angle and also bisects the opposite side, so that's going to be PR, and in the diagram there's only one of them. The center angle is the big one. Okay, so you've got P angle BPC. All right, and then finally find the measure of the central angle. Well, the way you're going to do that is just do 360 divided by 7 and round it up to one decimal place. So that's going to give you 51.4 degrees. Right, so now we're moving on to example 2, finding the area of a regular polygon. Again, look for the information. It's an octagon, so it's an 8-sided figure. The side length is 15 and the apothegm is 18.1. Well, the apothegm in this triangle that they've highlighted here is actually the perpendicular height. So you can go straight from that into the formula for the area of one triangle, which is the half base times height. Substitute your base and your height for 15 and the 18.1 that they give you. So the yellow triangle that they've highlighted is 135.75 square inches. But bearing in mind it's a regular polygon, so each of these triangles that's here, there are 8 of them in it. So what you've got to do is you've got to multiply 8 times the 135.75. So the total stained glass window will be 1086 square inches. So leading on from example 2, what they're trying to do here is they're trying to get you to work out the difference in the triangle. Okay, well, you know that it's a half base times height multiplied by the number of triangles. That's what we used as far as the stained glass window there was in example 2. But they're slowly working you through until eventually you get a complete new formula. Okay, so basically it's the half base times height, but slightly extended, so you can actually find, instead of having to multiply the area of one triangle by the number of triangles, if you rearrange it, you will find that all you've got to do here is the area equals 1/2 times the apothem multiplied by the perimeter. Okay, so now we've got a slightly new formula. A equals 1/2, a little a but a capitalized P. All right, so following on from example 2, we're going to go on to example 3 before we do any problems. But again, we need to find various parts of it. Okay, so it tells you it's a regular hexagon, it's a 6-sided figure, and it's told you that each side is 3. Well, the easy part is that you can do the perimeter, because 6 times 3 will eventually give you your 18, but you need your height. Okay, well, as per usual, you can make triangles, and if you bring that down into here and bisect it, you know that each triangle is 60 degrees. Well, if you bisect it, you've got a 30, 60, 90 triangle. Half of 3 is 1.5. You need the apothem, so the 1.5 is the shorter leg, the apothem is the longer leg, so it's going to be 1.5 times root 3. And then you just put that into your formula. That's the apothem. Use your calculator and come up with 23.4. It does say to the nearest tenth, so that's a good answer. Okay, well, that works for a regular hexagon, but for other regular shapes it doesn't. So what do you have to do this time? Well, now what you've got to do is obviously use some sort of trigonometry. Okay, example 2, or example B in this case, is a pentagon. Well, now you've got 72 degrees. All right, well, half of 72 is 36. You've been given various parts of it. Okay, so you can now use trigonometry instead of using your half AP. All right, but I want to look at this particular part here. Why 10? Well, because it is the fact that it is a pentagon, and in a pentagon you're going to make 2 triangles, 10 triangles, 2 triangles per side. Okay, so that's where this 10 comes from. Okay, and then using the rest of the information that you've got on there, you can find out what the apothem is. You know the angle, you've found the angle, you know the side. You need to use cosine in order to find the apothem, but you need to use sine in order to find the part of the perimeter that you want, the base of the triangle. Okay, so be careful. It's the second part one, the regular pentagon. You've got a little bit more information than you need to as far as example 3 is concerned. Okay, so let's do a few questions. So let's have a look at question number 2. All right, it's a regular shape. It's a equilateral triangle or equiangular. And again, if you put your auxiliary line in, and I'm going to rotate that, what you've got here now is the fact that you've got this guy here is 60 degrees. This one here will be 30. You know that this distance, according to this diagram, is 6. Okay, but what do you want now? You need to find the shorter leg, you need to find the longer leg. Well, the shorter leg from the hypotenuse is half, so this is going to be 3 meters. And then from the shorter leg to the longer leg, you multiply by root 3, so this is going to be 3 root 3. All right, now we've got all the information we need, and believe it or not, the one that we don't need is the 6 now, because everything else we've got. All right, so don't forget each side has 2 triangles, so we've got a equilateral, so we've got 6. So the first thing to do is quote the formula. A equals 1/2 AP. The half stays the same. The apothem we know is 3 root 3. And the perimeter is, well, we can use the 6. The 6 times 3 will give you 18. And again, it's calculator work. You plug all that into your calculator. And you'll finish up with 15.6 to the nearest tenth, and that's going to be meters squared. All right. Now, sometimes you've been given a lot of information, like question number 5. So if we go to question number 5 now, you know, we've got Kenton's job is community pool, but look at what we've got. Now we've got a regular octagon, but we've been given the information we want. So straight away we can quote the formula, a half AP, which is equal to the half. The apothegm that they've told you is 6, and I'm putting everything in parentheses, and then each side is 5, so 8 times 5 will give you 40. So again, if you do that, you will finish up with 120, and that's feet squared. Okay, so now we're moving on to example 4. This is find an area of composite figures, and we're doing it by adding. Okay, so obviously it's a multiple choice question. Which one of these is correct? Well, look at the diagram we've got. First of all, we've got the trapezoid, which is this guy here. We've got a triangle, which is this guy on this side, and obviously the semicircle, which is here. Each one has got its own distinct formula, and then it's just a case of substituting in, and make sure you add them together because you want to know the area of the whole thing. So the answer is 35.16, and it says, which is best represents the area. Well, the answer is going to be C. Alright, so now we're going to put example 4 into question. So this is question number 6. We've got what looks like the Star of David with a regular hexagon and 6 equilateral triangles. And all of the sides are going to be 5 inches according to the diagram. If you put the 6 triangles together, you will make another regular hexagon. So basically you've got 2 regular hexagons with sides 5. But I'm going to still do it exactly the same as you would have done on a composite shape. So the first thing I'm going to do is I'm going to start the triangle out first. Okay, the formula is A is equal to a half A base times height. Okay, but what I want to make sure is that we can break the triangles down. We know the hypotenuse is 5. Okay, well, if each angle is 60, so this guy here is going to be 30. This one here is going to be 60. Okay, so the hypotenuse to the shorter leg is going to be half, so this is going to be 2.5, and then from the shorter leg to the longer leg is just multiplying by root 3. So your height is going to be 2.5 radical 3. Okay, so let's put that in. So A equals 1/2. Don't forget the base is the whole of the triangle, so that's going to be 5. The height is going to be 2.5 radical 3. Okay, and don't forget you've got 6 triangles, so you need to put a 6 at the end so you can put it all together. Alright, now some of the answers are radical, so I'm going to leave it in radical until I can get one of these that's near. If it's not a radical, that way I can then put it in the calculator and see which one it is. But if I multiply all this lot out, 5 times 6 is 30, half of 30 is 15, and 15 times 2.5 will actually give you 37.5, and I'm leaving it at radical 3. Okay, now I did say that the triangles will make the same size as the hexagon, but let's do the hexagon. Okay, so here's the hexagon, and this is going to be A equals a half AP. Alright, so A equals the half. The apothegm is the same height as we had for the triangle, so that's going to be 2.5 radical 3. And this time the perimeter is going to be 6 times 5, that's going to be 30. Okay, so 30 times a half is going to give you 15. 15 times 2.5 will give you 37.5 radical 3. Okay, but we want the total area of the composite shape, so we're going to add the two areas together. So the total area is going to equal 75 radical 3. Okay, and that just happens to be one of the answers, so I don't need to change it in the calculator, so the answer to the question is D. Alright, so now we're moving on to example 5, area of a composite figure by subtracting. And as you can see here, we need also to find it to the nearest tenth. Well, the total shape is going to be a rectangle, and the part that's missing is going to be a triangle. Okay, now never assume that the height of the triangle is half the 5, so it's going to be 2.5. You do not know that. So never make that assumption. As you can see, you use Pythagoras in order to find the perpendicular height. Now you can find the area of the rectangle and the area of the triangle, subtract the two answers, and you finish up with 22.1 meters squared. Alright, so let's have a look at example 5 in its play. So this is question number 7, the basketball court. It's asking you for two different things. You want A, the area of the blue, and B, the area of the red. Now you can use some of the information from A in order to solve B a lot quicker. Alright, but let's have a look at what you've got. First and foremost, I'm looking at the shooting parts of the court. There are two of them. There are actually two rectangles, that's 12 by 19. And what you've got missing is just a semicircle on each end. So technically you've got a full circle, half from one end, half from the other end. So if we do two rectangles, subtract one circle, and then we've got to add the area of the circle right in the center of the court. So let's break that down and let's see what we can do. Okay, so first and foremost, let's do the rectangles. Well, that's 2 times the 19 times the 12. And put that in your calculator, you'll get 456. So that's the total, but we've got to subtract one of the circles. Okay, now the diameter is 12, so the radius is 6. So you've got pi r squared, so 6 is so pi r squared, and the radius is 6. So basically what you've got there is 36 pi. And if you subtract 36 pi from 456, you actually get 242.9, because the area of the circle is 113.1. Okay, so that's the two end parts of the court. Now we still need that little inside segment. Okay, and don't forget they've told you that the diameter is 6, so again it's pi r squared. This time the radius is 3, so we want 9 pi. And if you put that into your calculator, you get 28.27. And if you add them two together, so these two added together and rounded it up to the nearest whole number, you get 371 feet squared. Okay, so let's go through it again. The two rectangles, that's these two parts here. Take away a complete circle. We've got half a circle here, half a circle here, so that's the complete circle, which is that. Okay, so then we can subtract them, and that will tell you the area of the two ends. Then find the area of the center part of the circle and add them together, and you get a total of 371. All right, so now let's have a look at what we've got this time. Okay. So now we've got, if we look at what we've got now, technically, so there's A. Right, so for B, what we've got is a complete circle, 3 complete circles in respect, and all of them are 12 in diameter, so that's 6 in radius. And what we've got to do is subtract that. So we've got one circle here, we've got another circle here, we've got a complete circle here, but we've got to subtract what we got from the blue, which is this part here. Remember, this is the blue in the center. So if we do 3 circles and subtract 28.7, we'll get the answer. Okay, so now we've got the area equals pi r squared. Okay, and we need 3 of them. And then don't forget we've got to subtract the 28.7. Subtract 28.7 when we've finished. All right, so now it's just a number cruncher. So pi is, and the radius is 6, so this is going to be 3 times 36. It's going to give us 92 pi. Subtract the 128, so A for the red is going to give us 311 feet squared.